Hey everybody, welcome back. In this video, we're going to look at an example of a two-sample hypothesis test for the difference of population proportions. We are going to revisit the same example that we constructed a confidence interval for. This time we're going to perform a hypothesis test on it. So this is our binge drinker question, right? We have a population of men and women and a corresponding sample, right, of men and women with a p hat for both men and women. So the question wants us to perform a hypothesis test to determine if the population proportions are not equal. We will test at the 5% level. This is the level of significance. Oops. So in step 1, we write out our hypothesis, both our null and our alternate. So remember, we can write it this way, that the difference of the two is equal to 0, or we can just say P1 is equal to P2, right? We're always going to assume in our null hypothesis that they are equal to one another. If we were to add P2 to both sides of this expression, we would get the same exact thing here. So you can pick one way or the other to write it. You don't have to write both. I was just trying to be clear. And then our alternate hypothesis is that P1 minus P2 is not equal to 0, or just that P1 is not equal to P2. Okay. In step 2, same exact as a one sample hypothesis test, right? We state our alpha, or our level of significance, which we are given is 5% or 0.05. In step 3, we want to write out all of our statistics, and we have a few more. I'm going to go back a slide and use this table to write down all of our statistics. We have a few more, right, in these two sample problems. There's no really right or wrong way to, or order to write these down. I'm going to again choose men to be my first group and women to be my second group. So the sample size for men was 7,180. P hat 1 was, for the men, was 0.227. And then our sample size of women was 9,916. And P hat 2 was 0.17. This would probably also be a good place. If you recall from the last video, we're going to need our pooled results, right? So P hat pooled is actually given to us here. Remember, this is calculated by adding up the number of quote unquote yeses, right? Or the number in your sample with that desired trait you're looking for, right? Here, the trait we're looking for is, are you a binge drinker? So we're given that here. So if we add 1630 to 1684, we get 3,314. So the pooled, right, is 3,314. These two things added together. These two things. So this divided by this gives us this 0.194. That is our p hat pooled. The pooled sample size we'll write down as well. We do need to add the two sample sizes together later. That was 17,096. Okay. So there's kind of a lot of statistics to write out there. It's helpful to have them all in one place. So let's just try to remember men are our first group, women are the second group. Okay, so I'm going to come over here. We can start step 4. Start step 4A, right? Step 4 has two parts. We need to calculate our test statistic. And this is a little bit different. We have P1 hat minus P2 hat in the numerator. And just so that I don't get it wrong, let's go back a few slides. So we have our P hat pooled, right, over our first sample size plus P hat pooled times 1 minus P hat pooled over N2. I'm going to copy and paste this formula instead of writing it out just to save some time. Okay. All right, so step 4A, we need to calculate our Z value, right, which is a slightly different formula than what we've used before. So we can basically just plug everything in, right? We have P hat 1, 0.227. And not to confuse, but to just kind of show you all what we're doing is we're really comparing two differences to each other. So we have the difference in our sample proportions, right? P hat 1 minus P hat 2. This is some difference. And we're seeing how far away that is from the difference of our true population proportions, right? That difference between those two populations. You might be wondering, right, why do we only have sample statistics up here? Usually we take one sample statistic, right, subtract that from the population proportion or mean, right, in our null hypothesis. And so we're doing the same exact thing here, but now that we have two samples and two populations, we're comparing the difference between our two samples to the difference between our two population proportions from our null hypothesis, right? But what do we always, for these two sample hypothesis tests, we always assume that the difference between the population proportions is equal to 0, right? So this thing in here, we always assume it's 0, so we basically just aren't writing it. But in theory, it's there, it just is 0, so we don't write it out every single time. But I wanted to just mention that to show that it is similar, right, to what what we've done in other examples. So basically all we're left with is the difference between our samples. So we take that p hat 1, subtract from p hat 2, and then we take p hat pooled, right? 0.194 times 1 minus 0.194. I'm actually writing it out the other way. And I guess, oh yeah, we actually divide this by our individual sample sizes. And then we add this, same thing, 0.194, right? 1 minus 0.194. We divide that by our second sample size, 9,916. Remember, we're just calculating our z value here. Very similar, right, to what we've done before, just a little kind of extra steps. Okay, so let's find out what 0.194 multiplied by 1 minus 0.194 is. 1 minus 0.194. This on the inside is equal to 0.806. So I'm going to kind of erase this, do it step by step. 0.8, just because I'm running out of room. Okay, so that was 1 minus 0.194 was 0.806. We take 0.194 and multiply it by 0.806. We get 0.156. With a little bit of change. And then this will be same exact thing over here, right? P hat pooled times Q hat pooled. So this same exact thing we had. Now we have to divide 0.156 by each of our sample sizes. So now if I take 0.227, I'm going to rewrite this whole thing minus 0.17. I get a difference of 0.057 on the top. This is the numerator up here. Now let's do 0.156 divided by 7,180. I get 0.0. A very small number, right? 0.0000. 1, 2, 3, 4 zeros. 2, 2 about. And if we take 0.156 divided by 9,916, we're going to get another very small number, right? 0.00000. 1, 2, 3, 4. 1, 6. It's actually, let's write this out. 1, 5, 7 is what I get. Okay, so now let's add those two numbers together. 1, 2, 3, 4. So I'm adding 0.0000157 and 0.0000022. And we get 0.057 divided by, still haven't taken the square root, 0.0000377. So if we take the square root of this number, 0.0000377, I get 0.00614. So now if we divide 0.057 by 0.00614, we get a pretty large z value, right? I get 9.28. And I'm going to draw start part B, step 4 up here. It's a really bad drawing. So that's a z value, right? So we have a standard normal distribution with a mean of 0. So 9.2 is somewhere very far to the right of that. And try to pause here. Think, do we want the area to the left of this, the area to the right of it? Or do we have a two-tailed test? And what do we need if it is a two-tailed test? So to determine that, right, just like our previous one sample hypothesis test examples, we go back to our alternate hypothesis. The inequality is a not equal to sign here. So that tells us that this is a two-tailed test. So we need to find the negative 9.28 z value somewhere way over here. And we want the area under the curve to the left of that negative and to the right of our positive 9.28, right? So we want both tails. This just keeps going on and on forever. Same thing over here. So basically we can use our calculator to find this area or this area and just multiply it by 2, right? These will be equivalent. I'm guessing our calculator probably will not give us the actual area under the curve because the c value is so large, but let's try it anyway. So I'm going to go ahead and stop sharing my screen. And unfortunately, all of this will go away. But I will pull up my calculator here in just a second. I can find it. Give me 1 second. Here we go. Okay. All right. So you can go back to second bars, right, for our familiar distribution list. This is a normal distribution, right? So we're going to use the normal CDF function. Let's find the area under the curve to the left of negative 9.28, right? As we saw it in that drawing. So from negative infinity to negative 9.28, these are in terms of z-scores, right? So a standard normal distribution with a mean of 0 and a standard deviation of 1. Let's paste it in there, and yet it gives us a 0 So we need to multiply this by 2, right, to get the right-tailed, the area under the curve from positive 9.28 to positive infinity. But of course, 0 multiplied by 2 is just 0. So what we'll say for step 4, part B, is that our p-value is less than 0.001. And then in step 5, we compare our p-value, right, of 0.001 our p-value equals 0.001. This is less than or greater than our 0.05 alpha. It is obviously less, right? Smaller than alpha, which is 0.05. 0.001 is smaller than 0.05. So does anyone remember what we can conclude? To write this out. Step 6 is our conclusion. So we saw our p-value was smaller than our alpha, so we reject HO. There is significant evidence to suggest HA, right? The two population proportions are different. Or we can say are not the same. Okay. Let me see. Sorry if you can't see my screen. So yes, you should be able to see it now. This is our conclusion, right? We reject HO. We say there is significant evidence to suggest HA. Our alternate hypothesis, which is that the two population proportions are not the same. Okay.